Okay, so let's go ahead and continue with our lesson in 11-10. We are going to take a look at finding the Maclaurin series for the function f of x equal to the sine of x. Okay, so again, what we're going to have to do is we're going to have to start with our function f of x, which is equal to the sine of x. And let's go ahead and take the first few derivatives of this function. So the derivative of sine is going to be cosine. When we take the second derivative, we're going to wind up getting negative sine. The third derivative gives us negative cosine. And the fourth derivative takes us back to sine. Okay. Now we do see a pattern that emerges. However, I don't know that we can classify like this pattern here um, into a formula. We see that f is sine, the derivative f prime is cosine, f double prime takes us back to negative sine, f triple prime takes us back to negative cosine. The fourth derivative takes us back to our original function sine, and then subsequent derivatives are going to follow the same pattern. Okay, now if we want to find the Mach series for sine, that's going to be equal to the sum from 0 to infinity of the nth derivative at 0 over n factorial times x raised to the n power. Okay, so let's see if we can come up with a formula that's going to give us the nth derivative evaluated at 0. Okay, so let's take this function and the subsequent derivatives that we found, and let's evaluate the function and the subsequent derivatives at 0. So when we take f of 0, sine's value at 0 is going to be 0, f prime of 0. Cosine's value at 0 is going to be 1, f double prime of 0. Is going to wind up giving us 0, f triple prime at 0 is going to be negative 1. The fourth derivative at 0 is back to 0. And again, like we see a pattern that emerges. So we go from 0 to 1 to 0 to negative 1 back to 0. However, there's no way for us to like represent that pattern in a formula. Okay, so we're going to have to resort to doing something a little bit different here. Okay, so let's go ahead and let's take these values that we found over in here, and let's do our like Maclaurin series expansion utilizing the values that we just found. Okay, so we can say that the sine of x is going to be equal to, so the first term I get when I plug 0 in for n is going to be f of 0, which is 0, divided by 0 factorial, which is 1, multiplied by x raised to the 0 power, which is also 1. Okay, so 0 divided by 1 times 1 is going to wind up giving us 0, plus the next term we get is whenever we plug 1 into our summation for n. So that's going to be f prime of 0, which is 1, over 1 factorial times x raised to the first power. Okay, next term is going to be when we plug 2 in the place of n. So f double prime of 0 is 0 over 2 factorial times x squared. Let's do the next term as well. So f triple prime of 0 is going to be negative 1 over 3 factorial times x cubed plus let's just do the fourth one because we have that one already. So that will be the fourth derivative at 0, which is 0, over 4 factorial times x raised to the fourth power. Okay, so once we have this, we see that we have several terms that are going to wind up becoming 0. Okay, so let's go ahead and eliminate those terms in the series. Okay, so once we do that, the Maclaurin series that we wind up coming up with is the first term is going to be x. The next term is going to wind up becoming minus x cubed over 3 factorial. The next term, the next non-zero term is going to wind up being plus x to the 5th over 5 factorial. The next non-zero term is minus x to the 7th over 7 factorial plus, and then that summation is going to continue on forever. Okay, so what we are then able to do is we can take this remaining polynomial that we are left with, this infinite polynomial that we are left with, and express it using a summation. Okay, so the way that we can express this formula using a summation is this is going to be the sum from n is equal to 0 to infinity of, the first thing we should see looking at the polynomial that results is that the terms are alternating. So we have -1 raised to the n power. Okay, so the n is equal to 0 term is positive. The n is equal to 2 term is positive. So the even terms are positive, the odd terms are negative. So that's why we have -1 raised to the n power. And then the formula that's going to generate all of the terms in the series is going to be x raised to the 2n plus 1 power over the quantity 2n plus 1 factorial. Okay, and this right here is our Maclaurin series for the sine function. All right, and as we mentioned, the Maclaurin series for the function e raised to the x power is used a ton, and that is a formula that we should memorize. This one here is another formula that we should memorize as well. Okay, it gets used so frequently, you would want to memorize that formula also. Okay, so what I want you guys to do is I want you guys to use the same approach to figure out the Maclaurin series for f of x equal to the cosine of x. Okay, so you guys can go ahead and pause this video right now, work on this, and when you're done, unpause and see if yours matches up with what I came up with. Okay, so when we use the same approach for the max series for f of x equal to the cosine of x, our function f of x is equal to the cosine of x. Let's go ahead and take the first few derivatives of this. So f prime of x is equal to negative sine of x. F double prime is negative cosine of x. F triple prime is equal to the sine of x. And for the fourth derivative of x, that's back to our starting function of cosine. Okay, and again, if we're trying to find the max series for cosine, cosine of x is going to be equal to the sum from 0 to infinity of the nth derivative at 0 over n factorial times x raised to the nth power. Okay, so what we want to do here is evaluate the function and the first few derivatives at 0. Okay, so when we take f of 0, we get 1. F prime of 0 winds up giving us 0. F double prime of 0 is -1. The third derivative, f triple prime of 0, is 0. And the fourth derivative, evaluated at 0, we are back to 1. Okay, so if we want to like expand out our Maclaurin series, again, just like with the past problem, like we aren't able to write a formula that's going to generalize what the nth derivative at 0 is going to be, just with how that's written. Okay, so we're going to have to do a little bit of algebraic manipulation for us to get there. Okay, sorry, I don't want to write this in summation notation, but I actually want to expand out the first few terms. Okay, so when n is equal to 0, we get the 0th derivative at 0, so that's f of 0, which is 1, divided by 0 factorial, which is 1 times x raised to the 0 power, which is also 1. So that first term is 1. The n is equal to 1 term will be f prime of 0, which is 0, over 1 factorial times x to the first. Next term will be f double prime of 0, which is negative 1, over 2 factorial times x squared. The n is equal to 3 term will be f triple prime of 0, which is 0, over 3 factorial times x cubed. Let's go ahead and do one more because we have that listed already. So the fourth derivative at 0 is 1 over 4 factorial times x to the fourth. And that summation is going to continue on forever. Okay, so what we can do now is, just like in the previous example, if we eliminate all of the terms that have a coefficient of 0 in them, what we are left with is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on and so forth. And then what we can do is we can express that sum in summation notation. Okay, so this is going to wind up becoming the sum from 0 to infinity. We should see, looking at the polynomial that results, that the terms alternate, where the n is equal to 0 term is positive, n is equal to 1 term is negative, n is equal to 2 term is positive, n is equal to 3 term is negative. So we have negative 1 raised to the n power. And then the formula that generates all of the terms in the summation is going to become x to the 2n power over 2n quantity factorial. Okay, and as we said with the sine function, the max series for sine, we also want to memorize the max series for cosine as well, because it gets used so frequently on the AP test. Okay, now we can take what we discussed back in 11-9 and actually work through coming up with the max series for cosine even faster. Okay, so we know that the max series for sine is going to be the sum from n is equal to 0 to infinity of negative 1 raised to the n power times x to the 2n plus 1 power over 2n plus 1 quantity factorial. And from sine, if we want to get to cosine, we can take the derivative of the sine function to get cosine. Okay, so the derivative of sine is cosine, which means that if I'm going to differentiate that function, we can also differentiate the Maclaurin series. So when we do that, I'm going to work out the derivative over here to the right. I'll do it in light blue. So when we differentiate that formula, we get negative 1 to the n power times 2n plus 1 times x raised to the 2n power over 2n plus 1 quantity factorial, which means that I can cancel the factor of 2n plus 1 with the factor of 2n plus 1 on bottom. Well, if I have 2n plus 1 factorial, I can write my denominator as 2n plus 1 times the quantity 2n factorial. Okay, so I can cancel that factor of 2n plus 1 on top with 2n plus 1 on bottom. So then the formula for this summation becomes negative 1 raised to the n power times x to the 2n power over 2n quantity factorial. Now, normally when we differentiate a function, thereby differentiating the power series, what we do is shift the index 1 to the right. So you would think that you would shift your index over to n is equal to 1. However, we're not going to do that in this particular case, because if we take a look at the Maclaurin series for sine, I'm going to go to this step that we looked at earlier. In the Maclaurin series for sine, the first term in that Maclaurin series is x. So when we take the derivative of that first term, the derivative of that first term does not become, it's not like the first term is a constant where the derivative of that first term becomes 0, that first term goes away. When we differentiate that first term, the derivative of x winds up becoming 1, which is the first term in the Maclaurin series for cosine. Okay, so we don't wind up losing a term whenever we take the derivative of the Mach series for sine. Okay, so that's a way of us tying in this lesson in 11.10 with what we discussed back in section 11.9 when we looked at representing functions as power series. Okay, so we're going to do 2 more examples for this video, and then we'll move on to the next video, which is going to conclude, well, almost conclude 11-10. Okay, so this one asks us to find the Mach series for f of x equal to x times the cosine of x. Okay, so what we can do for this example is we know the Mach series for cosine is going to be the sum from n is equal to 0 to infinity of negative 1 to the n power times x to the 2n power over 2n quantity factorial. So if we want to find the Mach series for x times the cosine of x, all I need to do is multiply the Mach series that we just found for cosine by x. So we get x times the sum from n is equal to 0 to infinity of negative 1 raised to the n power times x to the 2n over 2n quantity factorial. And if we are distributing x across every single term in that sum, we can work x into that summation formula. So we get x times the cosine of x equal to the sum from 0 to infinity of negative 1 raised to the n power times x raised to the 2n plus 1 power all over 2n quantity factorial. And again, I'm not going to do an example with this, but if you wanted to determine the interval and radius of convergence, all you would have to do is use the ratio test and then what we discussed in section 11-8, where you establish the radius of convergence, write that as an inequality, a compound inequality to find the interval of convergence, and then you have to test your 2 endpoints to see if you have convergence or divergence at the endpoints. Okay, I want you guys to give this next example a try. So directions here ask you to find the Taylor series for the function f of x equal to 1 over x squared about x is equal to negative 1. Okay, so go ahead and pause the video while you do that. And then once you complete that, unpause and you can check your answer with what I come up with. Okay, so again, with this, we are going to take our function f of x. There we go, sorry. Okay, so f of x equal to 1 over x squared, which I'm going to rewrite that as x raised to the negative 2 power. Sorry, give me 1 second to plug in my charger for my laptop. I'm running low. Okay, I think we're good to go now. All right, so f of x is 1 over x squared, which is x to the negative 2 power. Let's go ahead and take the first few derivatives of this, see if we can see a pattern that emerges. So f prime is going to become negative 2, x raised to the negative 3rd power. F double prime would become 2 times 3 times x raised to the negative 4 power. F triple prime would be negative 2 times 3 times 4 times x to the negative 5th power. And I think that should be enough for us to see the pattern that emerges. So the nth derivative at x. So when I look, there's a couple of things that stand out to me. Okay, number one is this series is going to be alternating. So we have negative 1 raised to the r n is equal to 0 term is positive. The n is equal to 2 term is positive. So the even derivatives are positive. The odd derivatives are going to wind up being negative. So that tells me we have a factor of negative 1 raised to the n power. When I look at the factors out front, so for example, for f triple prime of x, we have 2 times 3 times 4. So I can write that as 4 factorial. So that's 1 larger than our derivative, so I'm going to make that as n plus 1 factorial. And then our exponent for x is 2 larger than the derivative, so I'm going to write in my denominator x raised to the n plus 2 power. Okay, so I'm going to do this with this problem. No, actually, I don't even have to. So if we're doing our Taylor series about x is equal to negative 1, then what we want to do is we want to take our nth derivative and evaluate it at negative 1. Okay, so that's going to give me negative 1 raised to the n power times n plus 1 factorial over negative 1 raised to the n plus 2 power. So whenever I simplify this, we have n plus 1 factorial all over negative 1 squared in our denominator. And negative 1 squared in our denominator is just 1, so I'm going to go ahead and get rid of that factor in my denominator. Okay, so if we want to get the Taylor series about x is equal to negative 1 for 1 over x squared, we can say that 1 over x squared is going to be equal to the sum from n is equal to 0 to infinity of the nth derivative at negative 1 over n factorial times x plus 1 raised to the n power. Okay, and all we're going to do is substitute the formula that we just came up with for the nth derivative at negative 1. We're going to substitute that into our summation. Okay, so we get 1 over x squared equal to the sum from n is equal to 0 to infinity of n plus 1 factorial over n factorial times x plus 1 raised to the nth power, and n plus 1 factorial over n factorial is just going to leave us with a factor of n plus 1 in the numerator. So we get n plus 1 times x plus 1 raised to the nth power. Okay, and that right there is our Taylor series for that function about x is equal to -1. Okay, so we'll continue on in our next video.